Okay, so I'm going to walk you through how to do this first assignment, because it's kind of just teaching you all how to use the tools and all that in the video and how to collect data. And then the second one, the Atlas launch, is what you'll actually be graded on. All right, but um, this first one, this first section of it is kind of just trying to get y'all used to how the video player works and all that, and the tools that you can use with it. So it's walking you through it, and we're just going to go through and follow the directions it gives us. So let's try making some measurements, blah, blah, blah. So it tells us to advance the video until the first frame where the ball is visible. So you can either click play and just wait, and then try and pause it when the ball comes out. And then these buttons to the left and right of the play button move it one frame at a time. So we can move it back until the ball is first visible. So that would be this frame right here. All right. What it wants us to do next is use the ruler tool to measure the distance between the ball and the can. So from the right edge of the ball, so the front edge of the ball, to the can, the left edge of the can, where it's closest to the ball. So to get the ruler tool, you're going to click here up on this tools in the top corner. You're going to click the ruler icon, and then you can drag this around until you line up the 0 with the right edge of the ball right there, just about. And then if we look at where it hits the left edge of the can, so the front of the can, it's at about 50, 51, 52 centimeters right there. All right, so this question, you can say that it's about 52 centimeters between the two of them. And click submit. It says we got it right. Hooray. All right, the other thing we're going to have to measure is the time. So once we've got the ruler in place, we can come back here and click on the tools again, and we can bring out the stopwatch. So when the stopwatch comes out, it's going to be telling us what time we're at currently. All right, and what we want to do is click right here to set this time where we first see the ball as t=0. So you can see how that zeroes it out and all that. So now we've got our measurement of distance and our measurement of time. And if we advance through the frames, you can see the time changes with each frame. So that's what we're going to be using to take our measurements for our data. All right, but at this current time, the question it's asking is how long it takes for the ball to move from the muzzle of the bazooka to the pop can. So we're going to advance this frame by frame until this thing hits the can. Hits the can right in that frame right there, so that's about 0.00269 seconds. So we'll look at the answers. That's that one right there. All right. Okay, this second section, the graphing directions, you click here and it opens it up. This doesn't have any questions to answer in it. It's just walking you through how to create the graph. All right, and we're going to do this exact thing down here. So I'm not going to read through all this. I'll just show you how to do it. All right, so to make our graph, we're going to do the same thing in this video that we did in the first one. We're going to advance the video until the ball comes out of the cannon. Just keep clicking. So this is the first frame right here. We're going to bring in our ruler and line it up right about there. And then we're going to bring out the stopwatch and zero it right at this first frame. Okay, we're going to name these columns. So this first column, we're going to say time, and the units of time is seconds. In the second column, we're going to say positions. That's how far the ball has traveled. And the position that we're measuring, the units here, is centimeters. So cm. All right, the other thing we need to do is convert that centimeters to meters. So you can either do that by hand, or you can set your columns up to do it for you. So what we're going to do is add another column by clicking this button right here, the 3 dots, and saying insert column right. And we can name this one position meters, like that, to remind ourselves what it is. All right, and then set your units to M. And then here, if you click the button again, this 3 dots, and go to go to change column formula, what you can do is set it to where it will automatically convert your position column from centimeters to meters. So to do that, we'll take position, and then to go from centimeters to meters, you divide by 100. So do that, divided by 100, and set that as the column formula. So now we can't type in here anymore. But if we put in something here, say 200, it should automatically fill in over here as 2, right? Because we had the 200 divided by 100 gives us 2. All right, so now we've got it converting automatically for us. Oops, that's not what I meant to do. Okay, so now we're just going to take some data, and we're just going to do this frame by frame. So we advance it 1 frame forward. We can look at where the ball is at. So if we started off at 0 right here at the front of the ball, we're looking at the front of the ball here, and we're at about, let's say, 8 centimeters. So we'll put an 8 there. And then our time for this frame right here is 0.00038. Okay, let me do it again for the next frame. Now we're at 0.00077. Oops. And our position, I'd say, is about 16. We're not quite there, but it's close enough. Maybe 15.5. All right, we go 1 more frame forward. Now we're at 0.00115. And our position, again, we're not quite at this 24. Let's call it 23.5. Go another frame forward. Our time is 0.00154. See, all these times are coming from this stopwatch tool up here. And we're at about 31.25, say. We're not quite at 32. We'll just call it 31.5. And these, you don't have to be super accurate with these, right? You're just kind of guessing based off of what you're seeing here. All right, so then we got 0.00192 as our time. And our distance here is about 39. All right, and it's asking us, or it told us up here, is that we want, sorry, I lost where it actually said it. Here we go. We want about 15 different times. So once we reach the bottom of this 5, you can click Insert Row Below and do that as many times as it takes. And we probably won't actually get 15. We're just going to do until a couple after it hits the can, right? So here, we go 1 more forward, 0.00231. And our distance here, this would be 45, 46, 47. Right, now we're at 0.00269. And it's a little hard to see, but let's say about 54.5. We're just going to keep on going, 0.00308. The front of the ball here looks to be at about 60.5. And the ball kind of got squished there, but let's at least go to 10. .00346. And now we're at about 66, I would say. .00385. That one looks like it's close to about 71. And we might as well do them all until the ball goes out of frame at least. Okay, so get the time for this frame. I'd say that's about 76, close to it at least. .00462. And we'll call that as close to 81. All right, and that's about as far as we can go. So we'll just get rid of these last three. All right, so you can see here how it is mapping out the time and the position for each of these on your little chart here. So this last section is going to be actually interpreting the data from your chart. So to do that, what you're going to have to do, first of all, is configure both your axes. So the time is fine, but actually on this left axis, we want our position to be shown in centimeters. So if we choose our vertical axis, we actually want to choose, we want our position to be shown in meters. So we actually want to click our little drop down member here and choose our position M column that we made. And it doesn't, it won't change the shape of it much because they're still proportional to each other. But what we can do now is click here to curve fits. And the curve that we want is the linear one. So we'll click that. And this will put in a line and give us an equation that matches our data. Oh, and I guess it wants you to put in variables here. So we can use t as our variable for position, for time. And then for our position, we can use p for position or d for distance or whatever you want. I just like using x, so I'm going to leave it as x. All right, and so what this tells us is that our position is equal to some variable times the time that it took plus a constant. All right, and our time, our variable for A here, the 175 that it shows us, what that means is that our ball was traveling at 175 meters per second. All right, and let's just walk through these questions. So describe the shape of your graph. Does the line of best fit go through all of the points? So we can say the graph is a line with a positive slope. And all that means is that as time goes up, position goes up too, right? We're going up and to the right. And it does not go through all the points. It gets close, but you can see there is some all right. So then what it wants you to do is to go through, and we're only going to care about the ping pong ball before it hit the can. So we're going to look back at the video and decide which frame it hit the can in. I would say it's this frame right here, the 0.00269, frame 7. So that means that everything after that, from frame 8 onwards, so this one, this one, this one, this one, and this one, if we click all those, it will ignore those data points. And you can see how now the line fits almost exactly straight through all these points, right? Whereas before, it was off a little bit on some of them. Some were under, some were above. But if we ignore all these points from after it hit the can and started slowing down, our line goes directly through all of these other ones. So it's a better line of best fit. So it's still a line with positive slope, but now it goes through all of the points. And I can't type very well. There we go. All right, so what it wants to know here is the slope of your line. So we're just going to go up here, look at our equation, and find the value for A. So this says 202, so our value here would be 202. Turn your slope into a for every statement. So for this, you're just trying to basically write it out in words. So we would say for every 1 second, the ball travels 202 meters. Does that make sense? Because every time that's what that slope means. Every time we increase our time by 1 second, we go 202 meters up. All right, the intercept, so that would be this value for B. And here we have the intercept being 0.00201 meters. All right, and then we just say, to turn that into words, we could say the position of the ball is 0.00201 meters when the time is equal to 0. And because our intercept is so tiny, I mean, it should be, right? Because we were trying to set it equal to 0. So this is fine. Does your intercept make sense? Say yes. We were attempting All right, and that attempting to set the intercept at 0, that's what we were doing when we were trying to line up the ruler with the ball on that first frame. So the fact that it's 0.00201 instead of 0 just means that we lined the ruler up a little bit off when we first started. So that's all there is to that. All right, and then all we're doing here is writing out the actual equation. So the equation should be in the form of x equals at plus b, and all we're doing is plugging stuff in. So we would say x equals 202t plus 0.00201 would be our actual equation here. And yours might look different if you use different variables or whatever, but it should be in the same format. So that's what it should look like. All right, then this very last question you kind of got to think about. So it's asking you, how did the velocity compare after it hit the can to before it hit the can? So in order to figure that out, what we're going to do is, instead of ignoring these points from after it hit the can, we're going to only care about those points from after it hit the can. So all the ones from before, we're going to click on to ignore them. And now you can see our line only goes through these points here, and it changes all this stuff in our equation, right? So this 132, the slope, the A value, that's your velocity. So before, our velocity was 202 meters per second, and after it hits the can, your velocity falls to 132 meters per second. So it actually goes down a ton, right? So if you're going to write this out in the format they want, which is a claim, evidence, and reasoning, we could say the velocity of the ball decreases from 202 meters per second before it hits the can to 132 meters per second after it hits the can. And I made a bunch of typos. This is shown by the line of best fit equation found using the data. I keep doing that. Collected in the video. Alright, so you could type out something like that. It doesn't have to be exactly that, but just something saying that the velocity went down from 202, which was our slope before, and then change what your graph is looking at, and then your slope of these points afterwards is 132. So that's what your new velocity would be. All right, then when you're done, you just click submit, and you're all finished. And then I mean, it's not going to show you that you're finished, because I've still got to go through and grade them, but that's what you're doing.